Okay. Okay, is the audio working? Can you hear me? Nobody said yes. Okay. I'd like to join in with the other speakers in thanking the organizers for a wonderful conference and for the invitation to speak. It's an honor. I'll be speaking about some work I've been doing with Frederick Deneff over the past 2 years on BPS state counting motivated by the OSD formula. And I'll be emphasizing the wall crossing behavior and something we call the entropy enigma. And I'll mention some recent work with Emmanuel Diaconescu. There's been a lot of activity in this general area over the past year, and I'll flash this set of references again at the end of the talk. So here's the outline. I'll set the scene, come to the main result, which is the wall crossing formula, and then describe 3 applications. 1 mathematical, then I'll go on to talk about counting D6, D2, D0 bound states. The main application is to a derivation of the OSD formula, which leads us to the entropy enigma. Time permitting, I'll say something about non-perturbative definitions of Z topological, and conclude with the riddle, which I think is important. So our setting is type 2A strings on a compact Calabi-Yau threefold X. The BPS states in 4 dimensions are wrapped branes of even dimension on X. These BPS states carry Ramond-Ramond charge. The charge today will be in the even cohomology of X. So P upper 0 is the D6 brane charge, lives in H upper 0. Capital P is the D4 brane charge. It's a degree 2 cohomology class. D2 charge, capital Q. D0 charge, Q little q naught, is a 6 form, or often identified with a number. Now, BPS states are characterized by having a Ramond-Ramond charge, but their existence depends on the boundary conditions on the moduli. The moduli of interest are the vector multiplet moduli B plus ij. B plus ij is denoted as T. T depends on X, and the boundary condition at infinity is T infinity. So these spaces of BPS states then depend on gamma as well as the moduli. As far as we know, they're finite dimensional. And already in the work of Zyberg and Witten, we knew that they depend on these moduli. Now, they are interesting. They account for black hole entropy. They play a key role in the OSD conjecture. It's today. They play a key role in quantum corrections to effective supergravity. They possibly carry interesting algebraic structures, generalizing Kac-Moody algebras, and finally they've played a role in recent attempts to categorify non-invariants. So we should study them. Now, the way we describe these, an important tool for describing these states are the n equals 2 central charges, so it sets some notation. The duality invariant product between electric and magnetic charges is denoted with these brackets here. The period vector is e to the t. That means I'm neglecting worldsheet instanton corrections, so today we're always working at large scalar class. Then the holomorphic central charge is the inner product of gamma and omega, and so that we can write that as an integral, and that's some cubic polynomial, and here's the normalized central charge. Okay. Now, already back in the work of Zyberg and Witten, based on earlier work in 2 dimensions by Cicciotti and Schilligater, Vafa, and others, we knew the basic mechanism by which BPS states decay and disappear from the Hilbert space. And what happens is you have a pair of charges, gamma 1 and gamma 2. You have a BPS state which is a bound state of other BPS states of charges gamma 1 and gamma 2. And when the central charges of those 2 constituents are aligned as complex numbers, then the state can decay. So this condition defines the marginal stability wall, denoted in this dashed line here. That's a real codimension 1 wall in moduli space. And let's imagine now that we change the moduli from one side of wall to the other, then we lose a space of BPS states. And here's the formula for the space of states that we lose. It's a product of the BPS states of charge 1 evaluated at the place where you cross the wall times the charge 2 times a representation of spin 3. And that spin is given in terms of the inner product of the charges. Some remarks about this formula. First of all, it depends, of course, on which direction you go. So the stable side of the wall is given by this inequality. Notice that nothing I've said here, notice that all I've used here are general properties of n equals 2d equals 4 supergravity. And so it's natural to conjecture that this is a universal formula. I'll say something about the proof in a moment. A useful corollary is to consider not the Hilbert space but the Witten index. And here's the formula for the change in the Witten index given by the product of those of the constituents times the dimension of that spin representation. Again, that's the symplectic inner product of gamma 1 and gamma 2. Now, this formula is only meant to apply when gamma 1 and gamma 2 are primitive. And moreover, it's only meant to apply when the place where you cross the wall is generic. Okay, how do we justify it? Well, there are three ways you can justify it. You can either study how D-brane moduli spaces change topology. That's hard, but we did it in some examples. I'll describe the proof in terms of macroscopic two-centered solutions. And then there's a nice discussion in terms of quiver quantum mechanics. Today we're only going to talk about the macroscopic proof. So that's based on Deneff's multi-centered solutions that figured in Jan de Boer's talk. Here you have a bound state of two particles of charges gamma 1 and gamma 2, and Deneff found a formula for the bound state radius in terms of the charges and the moduli. And the important thing about this formula is that in the denominator here you have the imaginary part of Z1, Z2 star. So that means that as the modulus crosses the wall, the imaginary part of Z1, Z2 star goes to 0, and that's a 0 in the denominator. And so this bound state radius gets bigger and bigger and bigger, and you literally see this state leaving the Hilbert space. Okay? Now, moreover, because the particles are far apart from each other, we know that the states that we're losing are the product of the states for this particle times this particle, but we must not forget that two dyons carry an electromagnetic field which has spin in it, and that spin factor is just the spin of the electromagnetic field. The formula can be generalized to the case where one of the charges is not primitive. Notice that the marginal stability wall for a pair of charges gamma 1 and gamma 2 is trivially the same as that for gamma 1 and n gamma 2. Okay, now what do the states look like with charges gamma 1 and n gamma 2 that decay as we cross this wall? Well, again, that's given from in Deneff's papers. The states look like this. You have a particle of charge gamma 1, and then all the particles of charges proportional to gamma 2 sit in a sphere of fixed radius, a kind of halo of gamma 2 type particles around this gamma 1 particle. So these are non-interacting, mutually BPS particles, and so they generate a Fock space. And if you sum up the Hilbert spaces that are decaying overall n, then you get a Fock space generated by these particles. The number of particles of charge k gamma 2 is given by this index here, weighted by a Landau level degeneracy. So when we calculate the change in the Witten indices for all these things, we get a generating function, which is a Fock space partition function given by this infinite product. And this infinite product is indeed the McMahon function in an appropriate circumstance, and very similar to the infinite products that appear in the Donaldson-Thomas and Gopakumar partition functions, although different, not exactly the same. That was the wall crossing formula. Let me now describe three applications. One is mathematical. It's a test, both a test and an application. It's a test because it applies to a situation in which the proof I just described doesn't obviously apply. Here we have a rigid holomorphic surface in a Calabi-Yau, and that's why it doesn't apply. It's not ample. It has a holomorphic bundle E on S, and let's suppose that E sits in a short exact sequence like this. Well, when that happens, mathematicians say that the bundle is unstable, and amusingly enough, that also means that physically, in the physical sense, it's unstable for an appropriate Kähler class. To study the change in the BPS states, it's convenient to generalize the Witten index to a two-variable polynomial by weighting the BPS states by their spin and R charge. The reason that's useful is that that polynomial is the Hodge polynomial for the moduli space of holomorphic bundles. And here's the formula then for the change in the Hodge polynomial. And that reproduces non-trivial results of Goethe and Yoshioka and goes beyond what they said and makes some new math predictions. And for me, the most surprising aspect of this was that the moduli space of D4 branes is not the moduli space of coherent sheaves, even when you neglect worldsheet instanton corrections. Let me go on now to the second application, where we're counting D6, D2, D0 bound states. So what is the charge of a D6, D2, D0 bound state? Well, I'll denote it by gamma of beta n. It has D6 brane charge 1, D2 brane charge beta, D0 brane charge n. For a BPS state, beta should be the Poincare dual of a holomorphic curve in X. And let's study the decay where one of these spits off a pure D2, D0 particle, gamma sub h. Well, to study this decay, let's make moduli space one-dimensional by taking B plus ij proportional to some vector p in the Kähler cone. So Z is a complex number. And in the complex plane, the walls of marginal stability look like this. So this was a big surprise. As long as beta h is non-zero, there's a wall of marginal stability that goes to arbitrarily large Kähler class. And that means that if we try and write a generating functional where we sum up all these indices for D6, D2, D0 bound states, it depends very strongly on T. And that should surprise many of you, because if you know anything about the Donaldson-Thomas invariance and you look at what they did, it looks for all the world like they're describing bound states of D6, D2, D0 BPS states. And indeed, it's true that this becomes the Donaldson-Thomas partition function, but only in a limit in moduli space. And that's good, too, because there are basically four flavors of Donaldson-Thomas partition function, and there are different ways in which you can take the limit. So the thing you should take away from this is that the partition function of D6, D2, D0 is counting atoms of gamma 2 particles around a gamma 1 particle. There are loads of walls of marginal stability up at large Kähler class. It's only when you go out to infinity that way or that way that you get the Donaldson-Thomas partition functions. And if you want to see the core states which don't have wall crossing, you should take b equal to 0 and go to infinity. Okay, let me now come to the OSD formula. So I think many of you have seen that many times. So it has the general form of the index is the Fourier transform of the square of the topological strength partition function. An important point is today I'm assuming that those indices should have something to do with large Kähler structure. So given that, the fact that there's all this wall crossing when the D6 brane number is non-zero means that this formula is very problematic for non-zero D6 brane number. And so we should put the D6 brane number equal to 0. Then the situation is much better. So now we're thinking that our charge gamma here is a D4, D2, D0 brane charge. Moreover, we'll take P in the Kähler cone, and we'll study this kind of limit. Well, a big surprise of only the last month or so is that this still has wall crossing. It depends on the direction in which you go out to infinity. But fortunately, our charge, gamma, actually chooses a direction in the Kähler cone. So now if we go out to infinity along P, we finally have an index which is well-defined, has no wall crossing, and is B independent. This is the index for which we should try and write an OSD formula. And Frederick and I, in fact, derived a formula of this type. You might call it a refined OSD formula. And it's, of course, a Fourier transform of a cutoff version of the topological string partition function. And one novelty is that there's a measure factor here. The measure factor had appeared in various other works in various other forms before. Our measure factor here has contributions which are just as large as worldsheet instanton contributions to z top squared, so it's really wrong to leave it out. Because this is cut off, there's an error. We give in a precise estimate for the error term. Okay, that's the refined OSD formula. I'm now going to explain a little bit about how we arrive at that formula. Getting there is most of the fun, actually. So the key is in the polar states. So what do I mean by polar states? Well, for a D4, D2, D0 charge, the first thing we should do is define a monodromy invariant D0 brane charge. Let's call that Q naught hat. And then up to a slight lie, these well-defined indices are functions only of capital P and Q naught hat. And therefore, we can form a generating function where we sum over the D0 brane charges. Now, this has the physical interpretation of a D3 instanton partition function, and therefore, by S duality, it's a modular form. And therefore, just as in Edward Witten's talk, the polar part of this modular form determines all of the non-polar parts. So what do I mean by the polar part? I mean the part which diverges as little tau here goes to I infinity. You see, I can't use a Q expansion because I've used Q for charges. Okay? So the pole is that tau goes to I plus I infinity. And there are a finite number of those terms. So the polar terms are Q naught hat positive. And then the black hole degeneracies, the infinite tail of the series, is Q naught hat less than 0. And those are all determined by the polar states. So we want to understand what these polar states are. So let's understand them both microscopically and macroscopically. So the microscopic description of the polar states is this. We have a D4 brane which wraps a surface S, and it has some U1 flux F on it and N anti-D0 branes. And then the D0 brane charge is given by a curvature term, the Euler character of the surface, plus half the anti-self-dual part of F squared minus N. This term and this term are non-positive and general negative, so Q naught hat is less than or equal to the maximal value, which is this Euler character over 24. We should be thinking of P as large, and in that case we have a large set of polar states. The polar states are the positive Q naught hat states. Now, what are these polar states macroscopically? What do they look like? Well, if you just try and plug into the attractor formula, you'll get an imaginary entropy, which is nonsense. And what that's telling you is that the polar states are not single-centered black holes. They are, in fact, these examples of these multi-centered solutions. In using the polar part to determine the black hole degeneracies, it's reasonable to think, and it's true, that the most important part, it's true for some charges, it's reasonable to think that the most important part are the ones with the strongest pole. Those we call the extremo polar states. Those are the ones with the largest positive value of Q naught hat that we can have. So we quantified that with this quantity epsilon here, and that's going to be the source of our cutoff. So we call an extreme polar state one for which epsilon is very small. And then this is what macroscopically the extreme polar states look like. They're bound states of these two kinds of atoms, the atom and the anti-atom. The atom is a D6 particle surrounded by a halo of D2, D0 particles. That's what extreme polar states look like. And so now we're ready to prove the OSD conjecture. So the first part is the fairy tale. So, our D4, D2, D0 brane partition function is a holomorphic function, and therefore given by its modular average of the polar part. The extreme polar part is an index, a partition function that counts these D6 anti-D6 bound states In order to write this, we need to put in this cutoff epsilon, so we make a mistake, and which we can control. And this depends on indices evaluated at a finite place in moduli space. Next, if we choose this epsilon to go to 0 sufficiently rapidly as p goes to infinity, then this partition function in fact splits as a product of D6, D2, D0 partition functions, and moreover, those can be identified with a cutoff version of Donaldson-Thomas. And then we have standard conjectures in the theory that Donaldson-Thomas is Gromov-Witten, which by definition is Z-top. So that's the sketch of the proof. Now, the important thing is that there's some limitations on the derivation here. The derivation depends crucially on using only those extreme polar states. And that translates into its validity only at strong topological string coupling, which in terms of the charges is given by this formula here. So it only applies when the D0 brane charge is much, much larger than p cubed. Well, that's fine. That's the region in which Maldacena, Strominger, and Witten were working. But there are other regions of charge space which are of physical interest. For example, you could take this D4, D2, D0 charge and scale up all the charges uniformly, and then G top goes to 1 over lambda G top. So as lambda goes to infinity, we exit the strong coupling regime and go into the weak coupling regime. And then the barely polar states, those with D0 brane charge of order 1, will contribute. And I made it sound like we were just stupid. We thought, we just didn't think of a proof which was good enough to apply to all charge regimes of interest. But we weren't that stupid, because there's actually a good physical reason why our derivation should break down, and that's the entropy enigma. It turns out that for suitable D2 and D0 charge, there are splits of gamma, or rather lambda times gamma, which remember is D4, D2, D0, into D6 anti-D6 bound states. Here are the charges, where moreover the D6 and the anti-D6 support single-centered attractors. So you can evaluate the entropy of this two-centered thing, and it scales like lambda cubed. On the other hand, you can arrange that this charge here also supports a single-centered attractor whose entropy scales like lambda squared, and that implies that the two-centered solution dominates the entropy. That's the entropy enigma. Now, it looks like trouble, because now that means that the log of the index has contributions going like lambda cubed, and it even has a lot of tension with the idea that black holes dominate the asymptotic degeneracy of states in string theory. But we shouldn't jump to conclusions, because while we found contributions to this index of order e to the lambda cubed, we cannot rigorously exclude the fact there are cancellations, because it's an index, bringing it down to order e to the lambda squared. In our paper, we argued extensively that that's unlikely, but we didn't prove it doesn't happen. We did reformulate that question. It's not an equivalence, but it's a moral equivalence. In terms of a very precisely formulated mathematical question in terms of the asymptotics of Donaldson-Thomas invariance. So we defined a critical exponent k by this formula here, and if k equals 3, that indicates that there is indeed the entropy enigma, and if k equals 2, that suggests that there are magical cancellations between these e to the lambda cubed states, bringing the index down to e to the lambda squared. Now, using some impressive progress in the computation of high genus Gromov-Witten invariance, Huang, Clem, Mourinho, and Tavanfar find numerical and tentative evidence that indeed k equals 2 and not k equals 3. But I think we'll hear about that from Albert's talk. But I think it's fair to say that the issue is open and important. What we can say today with confidence is the following. There's a degeneracy dichotomy. Either there are no magical cancellations, and then we have the entropy enigma, and we have to live with it and understand it. Or there are magical cancellations, and now let's explore what that means. The implications of that would be interesting. Well, the first point is we then have to confront the old problem of the absolute degeneracy of BPS states versus the index. You see, physically it's clear that when counting for the entropy, the dimension is the relevant quantity. On the other hand, all of the successful microstate entropy computations have used the index. Well, we are working in a moduli space approximation. We are neglecting certain non-perturbative string effects, So it's not unreasonable to think that Murphy's law will apply and everything that can get lifted will get lifted, and in the full theory the dimension is the index. Let's, for the sake of argument, accept that, and then explore what it means that if there are magical cancellations and the index goes like e to the lambda squared. Well, then what happens? We have these e to the lambda cubed states. They're not going to go away by tiny non-perturbative effects, but they might get lifted in pairs and not contribute to the index. So that means that the spectrum looks like at e equals 0 we have e to the lambda squared types of states, but at exponentially small energies we have many, many more states. So just to show that I can be fashionable too, we can call that a landscape of metastable states. Okay, I don't think we have time for this remark on the topological string. Let me conclude with a riddle. The riddle is, why did the BPS state cross the wall? Okay? You see, we want to understand black hole entropy. But we found lots of irrelevant stuff. Multi-centered states, core states, halos, some other things I didn't talk about called swing states. But we really want to understand the black holes. And the single-centered black holes always cross the wall. Now, it's true that with multi-centered solutions, they might or might not cross the wall, but those that always cross the wall, those that don't decay across walls, turn out to have macroscopic entropy. So we should count those too. So we really want to count the states which cross the wall, and we want to do that microscopically, so that's where the origin of the riddle comes from. We need to understand the answer to this riddle at the microscopic level. Okay, so with that riddle, I will leave you. That's the state of the art so far as I know it. And here again is the list of related references. Thank you.
Questions, remarks, riddles? Sure.
Yeah, this is probably a naive question, but if you have such a huge degeneracy of states at some tiny, tiny energy above the extremal states, if you computed finite temperature entropies but very low temperature, wouldn't you expect all these states to kick in and contradict agreements?
Absolutely. I would think that, So morally, the entropy would be e to the lambda squared at absolute energy equals 0, but I think it's inescapable that the effective entropy measured by an experimentalist is going to be e to the lambda cubed.
Further points? Everywhere. Yes, in the back. Annie.
How did it come about that the two-center solution played such a central role rather than three-center or four?
Yeah, right. I wish there were a snappy answer to that. So Frederick and I have some kind of complicated argument based on the fact that the attractor flow is a gradient flow for the absolute value of the central charge. So you come to the first split, and now you have two centers. Okay? And now, if you keep going down to three-centered or n-centered solutions, the z keeps decreasing. And so it seems unlikely to us that, in fact, a million-centered black holes will have even larger entropy, but we don't have a rigorous proof of that.
And if I could have another question. Is it surprising that something that you derived from these multi-center solutions, which after all are just leading supergravity solutions, that this formula ended up being an exact formula that you could use in the context of exact D-brane?
Well, okay, so you can, that's a good question, and that's why I was stressing that the formula makes no reference to anything except very basic quantities in n equals 2 supergravity, so you might think it's universal, and we got lucky. You can try and argue for this universality by saying, well, if you have a bound state of two BPS particles, they're marginally bound at the wall of marginal stability, so you can take them far apart. And so locality suggests that they should just be the product of the states here and there, plus the spin degeneracy of the electromagnetic field. The problem with that argument is that, at the very beginning, if you notice the spin, it had a quantum correction to that. And the only way I know to justify that quantum correction is by using a quiver quantum mechanics argument, which I don't know how universal that is. So I think it's a conjecture. Actually, that's one of the reasons I did that work with Iaconescu, to look at this wall-crossing formula in a case where it wasn't clear that the argument applied, and actually it applied amazingly well.
Okay, last question, Renata?
I have a comment. We have recently with Ferrara and Eric Gimon discovered very interesting multi-center solution in n=8 supergravity, where the issue of correction seems to be less severe than in n=2. And I also believe that better understanding of this universality and in general this multi-center BPS solution is still in front of us. And so I believe we will know much more, and they're very important.
Well,
particularly because in n=8, we know that quantum corrections are much less of a problem, but we just recently found those solutions.
well, I would say yes and no to that. I mean, yes, what you say is clearly true, but these multi-center solutions also played an important role in Ashok Sen's talk, but we didn't see the entropy enigma in Ashok Sen's talk, and probably the reason is in that case they actually cancel out. And so with a higher degree of supersymmetry, we might actually be missing some of the interesting phenomena we're after.
Yeah, I just wanted to stress that in n=8 case, when we're using quaternionic magic supergravity, please excuse me for this set of
Well, I'm sure.
miraculous words, it looks extremely impressive, and perhaps the most interesting story of all the black hole attractors I have seen. And I certainly would be interested to know how this all develops in n=2.
Okay, I suggest we close the discussion and thank Greg once more for his talk. And we now move up to the last speaker,